So the point of a Riemann sum is to approximate the area under a curve, which is also known as the integral. And the most common ways for doing this are the rectangular approximation method, also known as the RAM, and then the trapezoidal approximation method, which I don't think is known as the TAM, but I like to call it that. So the rectangular approximation method uses, as you might imagine, rectangles, which is this shape right here. And to approximate the sum, what you're going to do is add up the area of just a series of rectangles. So what we're going to do to approximate the area of this curve is add up a bunch of these areas. So it makes sense that we can use summation notation to write this. So we're going to start at interval 1. And we have 5 intervals here, so we're going to go up to 5. So for each of the rectangles, we want to find the area. And of course, we know that area is equal to base times height. Now in the context of this graph, your height is the value of this function at point C, and your base is the change in x on this interval. So to rewrite this, let's go ahead and put in our height, which is the value of the function at point C. And C, it's important to note, is inside interval I. And we're going to multiply this by the change in x in interval I again. So this is the basic notation for your generic Riemann sum. Now, what makes each approximation method unique is the location of C within the interval. So for the right Riemann sum, this point C is going to be at the rightmost part of every rectangle. And for the left Riemann sum, point C is at the leftmost part of every rectangle. For the middle, point C is in the middle of every rectangle. Hopefully you're catching on to the trend here. For the upper Riemann sum, point C is always just at the highest point in the interval, wherever that may be. So there's the highest, there we go. And then here on the negative side, we're still looking at the highest value. So that's going to be the least negative value. And then we have the opposite of that, which is the lower Riemann sum. And on this one, you're always going to go to the lowest value in the interval. And again, when we come over to the negative side, it's still the lowest number, so that's now going to be the most negative number. So for the trapezoidal approximation method, you need to remember the formula for the area of a trapezoid, which is 1 over 2 base 1 plus base 2 times your height. So and your bases are always just going to be the value of the function at the interval. And then to make your trapezoid, you just connect these. So what you're going to need to understand for the AP exam is how these under or over approximate the integral. So for the left and right Riemann sums, it's based on the first derivative. And then with the trapezoidal method, it's actually based on the concavity of the function, the second derivative. So rather than memorize all these rules, your best bet on those questions is really just to draw a quick sketch of your function. And then it should be pretty easy to see, you know, how a right Riemann sum would approximate, or the trapezoid would approximate. I mean, that's your best bet. So for the right Riemann sum, it's easiest just to start at the right end of the table and say this number is your height, and the difference between these two is your base. And you do that going down the line. And then for the left Riemann sum, it's just the inverse of that. So you start at the left and you say, here's your height, and the difference is your base. Height, base. So the middle sum is a little different because you can't use a standard interval like 1 to 2 because you do not have the midpoint value. So what you need to do on these is double the size of your rectangles. This way you'll have the middle value to use for the height. Now the trapezoid's a little different because you're going to be taking two bases and finding the average of them times 1/2, and then multiplying that by your height, which is now the difference in x. And then you do that going down the line. So it makes sense that if we would use smaller rectangles, we're going to get a much more accurate approximation. And ideally, with the most accurate Riemann sum possible, the base of these rectangles, or the change in x, is going to be infinitely small. So essentially what you have is an infinite number of rectangles. So the number on top here is just the total number of intervals. In our past example it was 5. But in just the basic formula, you have n intervals. So in this case, when the change in x is getting smaller and smaller, the number of intervals you have is approaching infinity. So we can write this as a limit as n approaches infinity. This is a pretty profound little formula we've come up with here, because this, as accurately as possible, determines the area under a curve. And guess what? We've actually seen another notation for this exact same formula, and it looks something like this. And you can see the parallels here. The infinitely small change in x correlates with the dx, and the value of the function at c correlates with just the value of the function at x. We can write the area under this curve as simply the integral of 3x squared plus 5x, or we can write it in this new notation. Now what if we didn't want the entire area? What if we just wanted the area from 0 to 1 of this function? So now we can say that the width in x is not just delta x. We can say that it is actually the width of our interval, which is 1, divided by n, which is the number of intervals. So hopefully I've covered everything Coach Lowe wants me to, and everything that you'll ever come across on the AP exam. So that's Riemann sums.